So let's take a look at finding area under polar curves. Now the formula is the area under a certain polar curve is going to be equal to 1/2 times the integral from a to b of r squared d theta. And so r is just going to be your given polar equation, while a and b are obviously going to be the bounds. And they are going to be in terms of theta, so they will be theta values. So let's say we have a certain given curve r, and we're trying to find the area under this curve. Notice how this curve is going from the angle of 0 all the way 180 degrees to the angle of pi radians. So our a value is going to be 0 and our b value is going to be pi, because those are our bounds of integration. Now keep in mind that sometimes when you integrate these polar equations, you're going to have to integrate something like sine squared of theta or cosine squared of theta. And we can't really integrate that, so we have to change it and use what's known as the half angle formula. So sine squared of theta can be turned into 1 minus cosine of 2 theta over 2, and cosine squared theta can be turned into 1 plus cosine of 2 theta over 2. So once again, the reason why we do this is so that it's easier to integrate, and we put it in this form. Now keep in mind that sometimes you might also get sine squared or cosine squared of 3 theta. Now since this just gives the formula for just regular sine squared of theta, if we get something more than theta, like 3 theta, or even half theta, or something other than just theta itself, all we're going to do is replace that for theta into our given formula. So instead of having cosine of 2 theta, we're going to replace theta with 3 theta, so then we'll get 1 minus cosine of 6 theta over 2. So once again, just replace the theta value with 3 theta. So then you'll get theta times 3 theta times 2, which is 6 theta. So let's say for number 1, we're given the graph of r equals 4 plus 3 sine theta, and we're trying to integrate the right half of that graph. So once again, if I were to write the formula, the area is going to be equal to 1/2 times the integral from a to b of r squared d theta. So we are already given our r, so we're already good with that. We need to find our a and b values. So at what theta values or are our bounds? So notice how we are going from negative pi over 2 all the way to a positive pi over 2, a positive 90 degrees. So those will be our a and b bounds. So if I were to rewrite the formula here, the area is going to be equal to 1/2 times the integral. Our a is a negative pi over 2, and the b is positive pi over 2 of r squared. So if our r is 4 plus 3 sine theta, then we're going to have 4 plus 3 sine of theta, and the entire thing squared, d theta. So in order to integrate this, we must FOIL 4 plus 3 sine theta squared. So we'll get 1/2 times the integral of 16 plus 24 sine of theta plus 9 sine squared theta d theta. So notice we do have sine squared here, and we can't integrate that easily, so we must use the half angle formula. Once again, sine squared of theta is equal to 1 minus cosine of 2 theta over 2. So we can just go ahead and replace that with sine squared. So we'll get, if I were to just replace 9 times sine squared, we'll get 9 times 1 minus cosine of 2 theta over 2. Now I'm just going to go ahead and distribute the 9 and simplify. So we'll get 9/2 minus 9/2 cosine of 2 theta. So if I were to rewrite the integral, we'll get 1/2 times the integral. Once again, our bounds are from negative pi over 2 to positive pi over 2. of 16 plus 24 sine of theta plus 9 halves minus 9 halves cosine of 2 theta d theta. So notice we do have like terms here, 16 and positive 9 halves. So if I add them together, 16 is 32 over 2, and 32 over 2 plus 9 over 2 is 41 over 2. So I'll rewrite the integral once again. Plus 24 sine of theta minus 9 halves cosine of 2 theta d theta. And now finally we can integrate. So I'm just going to go ahead and remove most of this stuff here. So the integral of 41 over 2 is obviously just 41 theta over 2. So we get 1/2 times 41 theta over 2, or 41 over 2 theta, plus the integral of 24 sine theta, which is negative 24 cosine of theta, because we derive negative cosine to get to positive sine. And the integral of negative 9 halves cosine of 2 theta is going to be negative 9 over 4 sine of 2 theta, because the derivative of negative sine is negative cosine. And so we're going to go from the bounds of negative pi over 2 to positive pi over 2. So now I can just plug it in and evaluate. So I'm just going to separate the 1/2 for a little bit and just evaluate what's inside, because I can always multiply by 1/2 when I get the final answer. So when I plug in pi over 2, we'll get 41 pi over 2 times, or divided by 2, which is 41 pi over 4, minus 24 times cosine of pi over 2, and cosine of pi over 2 is 0, minus 9 over 4 times sine of 2 times pi over 2, or sine of pi. And sine of pi is obviously 0. So we'll get 9 over 4 times 0, minus, when I plug in negative pi over 2, so we'll get negative 41 pi over 2 divided by 2, which is negative 41 pi over 4, minus 24 times cosine of negative pi over 2. And remember, negative pi over 2 is the same thing as 3 pi over 2. And cosine of 3 pi over 2 is 0. Minus 9 over 4 times sine of 2 times negative pi over 2, or sine of negative pi. And sine of negative pi, or same thing as saying sine of positive pi, is obviously 0. So I'm just going to go ahead and replace that with a 0. So now we could just have a bunch of things that cancel here, since they're being multiplied by 0. So in the end, we'll get 41 pi over 4 minus a negative, so plus 41 pi over 4. Don't forget that we have a 1/2 out front, so we always have to include that. 41 pi over 4 plus 41 pi over 4 is 82 pi over 4. So then multiply by 1/2, we'll get 82 pi over 8. And that just simplifies back down to 41 pi over 4 units squared. So now for number 2, we have r squared equals 4 cosine of 2 theta. Now if I were to graph it, or graph this polar curve here, we would get something close to infinity sign. So let's say for number 2 now, we have r squared equals 4 cosine 2 theta. And when you graph this, you basically get an infinity sign. Now, in order to find the area of this entire curve here, we can do a couple different methods. We can find the area of the entire curve, we can find the area of half of it and multiply by 2 to find the full area, or we can even find a quarter of it and multiply by 4 to find the full area. But in this case, I think it's easiest to find half of it and multiply by 2. So notice how this curve goes from this angle here all the way to this angle. So we need to find those bounds, and those will become our A and B bounds. So notice how at those specific angles though, the value is 0. The R value, because the radius is 0. So in order to find where the radius is 0, we can basically set this equation equal to 0, or put 0 for R. So 0 squared, or just simply 0, is going to equal 4 cosine of 2 theta. Now divided by 4, obviously 0 equals cosine of 2 theta. Now in order to find this, I can first find where cosine of theta equals 0. So cosine of theta equals 0 at the theta values of obviously pi over 2 and 3 pi over 2. But since it's asking for cosine of 2 theta, I can divide both of those values by 2. And so our real theta values are going to be at pi over 4 and 3 pi over 4. So obviously 3 pi over 4 is this angle here. So we don't really need that, but we do need pi over 4 because that is what our B value is. Now since this graph, even though my drawing doesn't show it, obviously this graph is symmetrical about both the x and y axis. So our A value, if B is pi over 4, then our A is obviously negative pi over 4. So those will be our bounds of integration. So now if I were to write the integral, or the area formula, it's going to equal 1/2 times the integral from A to B. Once again, our A is negative pi over 4, and our B is pi over 4, of R squared. Now keep in mind that we are already given R squared, so we just need to replace that. We get 4 cosine of 2 theta d theta. Now keep in mind this is the area for 1/2 of this curve. So in order to find the full area, we can just multiply by 2. And notice it will get rid of this 1/2. So the real area formula here is going to be the integral from negative pi over 4 to pi over 4 of 4 cosine of 2 theta d theta. So in order to solve this, we're going to take the integral of 4 cosine 2 theta, and the integral of 4 cosine 2 theta is going to be 4 over 2, or just 2 sine of 2 theta, because the derivative of sine is cosine. And obviously our bounds are from negative pi over 4 to a positive pi over 4. So now I can go ahead and just plug this in. So we get 2, I'm just going to leave the 2 outside, and we're going to get sine of 2 times pi over 4, which is pi over 2, minus, when I plug in negative pi over 4, which is sine of 2 times negative pi over 4 and negative pi over 2. So then we get 2 times sine of pi over 2, which is 1, minus sine of negative pi over 2, or sine of 3 pi over 2, which is a negative 1. So we have a minus a negative 1, which is plus 1. Then obviously we get 2 times 2. That's going to give us 4 units squared. So let's take a look at finding the area between two polar curves. And so the formula for that, the area is going to be equal to 1/2 times the integral from A to B of f of theta squared minus g of theta squared. And so f of theta refers to the outer curve and g of theta refers to the inner curve. So we're basically doing the outer curve squared minus the inner curve squared. Now sometimes there won't necessarily be an outer curve and an inner curve, so in that case we're going to have to split it up into 2 different integrals with 2 different bounds. So the area is going to be 1/2 times the integral. This one's going to be from A to B of one of the curves squared, plus 1/2 times the integral from C to D, so 2 different bounds of the other curve squared. So for number 1, we have to find the area inside the first curve and outside the second one. So if I were to draw r equals 4 sine theta, it's going to look something like this. And r equals 2 is just a circle with a radius of 2. So if I were to draw these two graphs, it would look something like this, where 4 sine theta is the outer one. So if I were to draw these two graphs, it would look something like this, where 4 sine theta is the top one and r equals 2 is the bottom one. And so notice it says find the area inside the first curve and outside the second one. So we're basically looking for inside 4 sine theta, but outside r equals 2. So this is the area we're trying to find. So in this case, since we do have an outer curve and we do have an inner curve, we can go ahead and use our formula. So once again, the formula, area is going to be equal to 1/2 times the integral from a to b of the first curve, f of theta squared, minus the second curve, g of theta squared. So if I were to graph these two curves, this is what it would look like, where 4 sine theta is the top one and r equals 2 is the bottom one. And so we're trying to find the area inside the first curve and outside the second one. So if the first curve given to us is 4 sine theta, and we're looking to go inside this one, but outside r equals 2. So this is the area we're trying to find. Since there is an outer curve and an inner curve, we can use our formula. So once again, the formula for the area is going to be 1/2 times the integral from a to b of f of theta, the outer curve squared, minus g of theta, the inner curve squared. And so we need to identify our a and b bounds. And those are just going to be the points of intersection of these two graphs. Notice the points of intersection are here and here. And in order to find those, we can basically set these two equations equal to each other. So if 4 sine theta is going to be equal to 2, then the sine of theta is going to be equal to 2 over 4, or 1/2. And sine of what value gives us 1/2? Well, that is going to be at pi over 6 and 5 pi over 6. And if you want to double check, notice this is the angle approximately of pi over 6. And over there is also approximately the angle of 5 pi over 6. So now when we write the formula, the area is going to be equal to 1/2 times the integral from a to b. So our a bound is going to be from pi over 6, and we're going to go all the way to 5 pi over 6, which is the b bound. So a is once again pi over 6, and b is 5 pi over 6. Now f of theta is just going to be the outer curve, and the outer curve in this case is 4 sine theta. So we're going to do 4 sine of theta, the entire thing squared, minus the inner curve, which is 2, and 2 squared is simply just 4. So to simplify, I'm just going to go ahead and FOIL, or just square 4 sine of theta. So we're going to get 16 sine squared of theta minus 4. And so that is going to be our integral. And remember, when we integrate something like sine squared or cosine squared, we can use the half angle formula. So sine squared can be turned into cosine, or 1 minus cosine of 2 theta over 2. I can go ahead and distribute the 16, and 16 over 2 is 8. So we'll get 8 times 1 minus cosine of 2 theta, and when I distribute it, we get 8 minus 8 times cosine of 2 theta. So then when I rewrite the integral, we'll get the integral, we'll get 1/2 the integral from pi over 6 to 5 pi over 6 of 8 minus 8 cosine squared, or sorry, cosine of 2 theta, minus 4 d theta. And once again, 8 minus 4 is 4. We'll get 1/2 the integral from pi over 6 to 5 pi over 6 of 4 minus 8 cosine of 2 theta. And so now we can integrate. So the integral of 4 is just 4 theta, and the integral of negative 8 cosine of 2 theta is negative 4 sine of 2 theta. And don't forget, we do have the 1/2 out front, so if I distribute the 1/2, we'll get 2 theta minus 2 sine of 2 theta. And once again, our bounds are going from pi over 6 to 5 pi over 6. And so when I go ahead and plug in 5 pi over 6, we'll get 10 pi over 6, or 2 times 5 pi over 6, minus 2 times sine of 2 times 5 pi over 6, or sine of 10 pi over 6, minus when I plug in pi over 6. So then 2 times pi over 6 is obviously 2 pi over 6, or pi over 3, minus 2 times sine of 2 times pi over 6, or pi over 3. Now 10 pi over 6 can be simplified to 5 pi over 3, minus 2 times sine of 5 pi over 3. And I'm just going to rewrite pi over 3 and minus 2 sine of pi over 3. So we get 5 pi over 3 minus 2 times sine of 5 pi over 3. And sine of 5 pi over 3 is negative square root of 3 over 2. Minus pi over 3 minus 2 times sine of pi over 3, which is square root of 3 over 2. Notice the 2's will cancel here and the 2's will cancel here. So we're basically going to end up getting 5 pi over 3 minus a negative, so plus the square root of 3, minus pi over 3 minus the square root of 3. Now 5 pi over 3 minus pi over 3, it just gives us 4 pi over 3. And the square root of 3 minus a negative square root of 3, or plus square root of 3, will give us 2 times the square root of 3. Units squared. And that should be the final answer. And so for number 2, we have r equals 3 cosine theta and r equals 1 plus cosine theta. And so if we're trying to find the area inside the first curve, which is r equals 3 cosine theta, and outside 1 plus cosine theta, then we'll be looking to find this shaded area here. And since there is an outside and an inside curve, we can use this formula. And so we are already given the f of theta and g of theta. And so we need to find our 2 points of intersection, or our bounds from A to B. And notice these are our 2 points of intersection. So in order to find those, similar to the last problem, we can just set it equal to each other. So 3 cosine theta can be equal to 1 plus cosine theta. If we subtract over the cosine theta, I'll get 2 cosine theta equals 1. So then cosine of theta equals 1/2. Now at what values does cosine of theta equal 1/2? Well, that's going to be at theta equals pi over 3 and 5 pi over 3. And as shown in this graph, we can see that it's about 60 degrees at pi over 3. And the other one is about at 5 pi over 3, even though my graph doesn't show it as good. So now we can write our formula. So the area is going to be equal to 1/2 times the integral from A to B. Now be careful when you choose the A and B value here, because if we choose pi over 3 as our A and 5 pi over 3 as our B, we're going to start from pi over 3 and go all the way to 5 pi over 3. So then we'll be accounting for this area. But we don't want to account for that area. We want to account for the shaded area here. So instead of putting 5 pi over 3, we can rewrite it as negative pi over 3. And switch that so that negative pi over 3 is our A value, and we're going to start from negative pi over 3 and go to pi over 3, our B value. Because if we do that, we start from here, and we're going to go all the way to positive pi over 3. And that will account for this shaded area here. So our integral from 1/2 times from negative pi over 3 to pi over 3, positive pi over 3, of f of theta, which is the outer curve, so 3 cosine theta, squared, minus g of theta, or 1 plus cosine theta, squared, d theta. So I'm just going to go ahead and start by squaring both of these. So 3 cosine theta squared This can be 9 cosine squared of theta. And if I FOIL 1 plus cosine theta, I'll get minus 1 squared, which is 1, plus 2 cosine theta, plus cosine squared of theta. And if I distribute the negative, we'll get 9 cosine squared theta, minus 1, minus 2 cosine theta, and minus cosine squared theta. And so 9 cosine squared minus 1 cosine squared will give us 8 cosine squared theta, minus 1 minus 2 cosine theta. So then if I were to rewrite that in the integral, we get 1/2 times the integral from negative pi over 3 to positive pi over 3 of our integral here. And remember, since we have cosine squared, we need to use our half angle identity or half angle formula. So cosine squared is going to be equal to cosine of 2 theta plus 1 over 2. 8 over 2 is 4, and if I distribute the 4, we'll get 4 cosine of 2 theta plus 4. And so if I add these other ones, then we'll get minus 1 and minus 2 cosine theta, and then 4 minus 1 is 3. So our integral will look like 4 cosine 2 theta plus 3 minus 2 cosine of theta. So rewriting the integral, we get the integral 1/2 times the integral from negative pi over 3 to a positive pi over 3 d theta. And so now we can integrate. So the integral of 4 times cosine of 2 theta is 2 sine of 2 theta. The integral of 3 is just 3 theta. And the integral of the negative 2 cosine theta is negative 2 sine of theta. So I'm going to add the 1/2 out front. And to evaluate, I'll distribute the 1/2, so we'll get sine of 2 theta plus 3 theta over 2 minus sine of theta. And so to evaluate, we're going to go from the bounds of negative pi over 3 to positive pi over 3. So when I first plug in pi over 3, we'll get sine of 2 pi over 3 plus 3 over 2 times pi over 3, so then 3 pi over 6, or pi over 2, minus sine of pi over 3. Now minus when I plug in negative pi over 3, so we'll get sine of negative 2 pi over 3, minus 3 pi over 6, or minus pi over 2, minus sine of negative pi over 3. So now if I were to evaluate, the sine of 2 pi over 3 is just the square root of 3 over 2, plus pi over 2, minus sine of pi over 3, and sine of pi over 3 is also square root of 2 over 3, or square root of 3 over 2, minus sine of negative 2 pi over 3, which is negative square root of 3 over 2, minus pi over 2, minus sine of negative pi over 3, which is also negative square root of 3 over 2. But since we have minus and negative, then it's just going to be plus square root of 3 over 2. Notice square root of 3 over 2's will cancel. And so all we're left with is pi over 2 minus a negative pi over 2. So plus pi over 2. And so that gives us 2 pi over 2. So a final answer of pi units squared as the final area. So now let's take a look at finding the area between sine of theta and cosine of theta. So I've already drawn the graphs here below, and so we're trying to find this area between both these graphs. And notice how there isn't necessarily an outer curve and an inner curve, so we can't use the formula where we have to take the outer curve squared minus the inner curve squared. But instead we can write two different integrals. So one for sine of theta and one for cosine of theta. And so notice how there is an intersection point here, so we have to find what that intersection point is first. So if I were to write out the integral here, or the formula for the area, we're going to do 1/2 times the integral from a to b of f of theta, or one of the curves squared, plus 1/2 times the integral from two other points of the other curve g of theta squared. So in order to find that point of intersection, we can just set sine of theta equal to cosine theta. And so we need to find where does sine of theta and cosine theta have the same value. And that is going to be at theta equals pi over 4. Because at pi over 4, both sine and cosine have the value of square root of 2 over 2. And so looking at here, this is the angle pi over 4. Let me redraw that. Around 45 degrees. And so what we can do with this is set up an integral to find the area of this portion of sine, and then set up another integral and add that so that we can find the area of this portion of cosine. So if I were to write out the area for sine first, you can put 1/2 times the integral of f of theta, so sine of theta squared, which is sine squared of theta. And in order to find the a and b bounds, notice we're starting at 0 here, at the center, and going to pi over 4. So our bounds are from 0 to pi over 4. And then we can add the graph for cosine of theta. So we get 1/2 times the integral of g of theta. So if g of theta is cosine theta, and square that, so we get cosine squared of theta. In order to find our bounds, for cosine theta, notice we're starting at pi over 4 and going to 90 degrees, or pi over 2. So we're going to go from pi over 4 to pi over 2 of cosine theta, or cosine theta squared. So now that we have the formula, let's first start out by integrating sine of theta squared. So we get, remember we have sine of theta squared, so in order to make it easy to integrate, we must use the half angle formula. So we can rewrite sine squared of theta as 1 minus cosine of 2 theta over 2, or the same thing as 1/2 times 1 minus cosine of 2 theta. So if I rewrite the integral, we get 1/2 times the integral from 0 to pi over 4 of 1/2 times 1 minus cosine of 2 theta d theta. 1/2 is a constant, so I can take that outside the integral, and 1/2 times 1/2 is 1/4. So I end up getting 1/4 times the integral from 0 to pi over 4 of 1 minus cosine of 2 theta. So the integral of 1 is just theta minus the integral of cosine of 2 theta, which is 1/2 sine of 2 theta. And then we have multiplied by 1/4 on the outside. So we get 1/4 theta minus 1 over 8 sine of 2 theta. And we're going to evaluate once again from 0 to pi over 4. So when I plug in pi over 4 first, we'll get pi over 16 minus 1 over 8 times sine of 2 pi over 4, or sine of pi over 2, which is 1, minus, when I plug in 0, so we'll just get 0 minus sine of 2 times 0, which is still 0. So that will be out, or that can cancel. So we're left with pi over 16 minus 1 over 8. And if I want to combine those two fractions, we do pi over 16 minus 2 over 16. So then we'll get pi minus 2 over 16 as the integral of from 0 to pi over 4 of sine squared of theta times 1/2. So now in order to find the integral of cosine squared, we need to change it like sine squared so that it's easier to integrate. So cosine squared of theta is going to be equal to cosine of 2 theta plus 1 over 2, or the same thing as 1/2 times cosine of 2 theta plus 1. And so when we take the integral of that, the 1/2 is a constant, so I can bring it outside. and we have 1/2 on the outside as well. So then we can rewrite it as 1/4 times the integral, this time from pi over 4 to pi over 2 of cosine of 2 theta plus 1. Now the integral of cosine of 2 theta is 1/2 sine of 2 theta. And the integral of 1 is just theta, so plus theta. We have a 1/4 on the outside, so we get 1/8 sine of 2 theta plus 1/4 times theta. And we're going to evaluate from pi over 4 to pi over 2. So when I plug in pi over 2, we'll get 1/8 times sine of 2 times pi over 2, which is pi, plus 1/4 times pi over 2, or pi over 8, minus, when I plug in pi over 4, so then we get 1/8 times sine of 2 pi over 4, or pi over 2, plus pi over 16. So then sine of pi is obviously 0, so times 0 times 1/8 is obviously 0, so that'll cancel out. So then sine of pi over 2 is 1, and 1 times 1/8 is 1/8. So we get 1/8 plus pi over 16, and then we have pi over 8. And pi over 8 minus that, so then when I evaluate, we'll get pi over 8 minus 1/8 minus pi over 16. And I can change all of them to have the denominator of 16, so I can add or subtract these fractions. So then we get 2 pi over 16 minus 2 over 16 minus pi over 16. And so finally, when I evaluate, 2 pi minus pi is just regular pi. So pi over 16 minus 2 over 16. So then we get pi minus 2 over 16 as the integral of 1/2 times cosine squared of theta from pi over 4 to pi over 2. So now that we have found 1/2 times the integral of sine squared and 1/2 times the integral of cosine squared, we can add these two together. So then we'll get 2 pi minus 4 over 16. And so to simplify, we can just divide each term by 2. So then we'll get pi minus 2 over 8 units squared as the final answer for the area between r equals sine of theta and r equals cosine theta. So let's take a look at finding polar arc length. Now the formula for polar arc length is L equals the integral from a to b of the square root of r squared plus dr over d theta squared. D theta. And so r is obviously going to be our given equation, or given polar equation. The dr d theta is basically the derivative of r, so I just normally write it as r prime, because we know it's just going to be the derivative of our given equation. And so obviously a and b are going to be the bounds in terms of theta. So let's say for number 1 we have r equals theta squared, and we're trying to find the arc length. So looking at the formula, we already have r, so now we need to identify r prime. And so we just need to take the derivative. So if r equals theta squared, dr d theta, or r prime, is simply just going to be equal to 2 theta. And so now, in order to find our a and b bounds, we need to be able to graph the equation. So if I were to graph this using my calculator, on a large scale I would get something like this. The graph of r equals theta squared. So notice that we start at the value of 0, because the theta value is 0, and we're going one full revolution all the way to 2 pi. So we're starting at 0, that is our a value, and we're taking one full revolution all the way to 2 pi, which is going to be our b value. So in order to write the formula, the length of this specific polar curve is going to be equal to the integral from a, which is 0, because that is our starting point, all the way to our b value, which is 2 pi, of the square root of r squared. So if r is equal to theta squared, then r squared is going to be equal to theta to the 4th power, plus r prime squared. So if r prime is 2 theta, then square that and you get 4 theta squared. The square root of that d theta. So in order to integrate this, we need to be able to factor out theta. So if I were to, I'm just going to ignore the integral for right now and just focus on the square root. So if I factor out theta squared inside the square root, we'll get the square root of theta squared times theta squared plus 4. And since these two are being multiplied here, the square root, we can take the square root of theta squared, which is obviously just theta, and that'll come out of the radical. So we'll get theta times the square root of theta squared plus 4. So now if I rewrite the integral, we'll get the integral from 0 to 2 pi of our rewritten integral, theta times the square root of theta squared plus 4 d theta. And now this is just a simple u sub problem. So if I were to use u substitution, I'll make u equal to theta squared plus 4, which means du, or the derivative of the u, will be 2 theta d theta. So then to isolate d theta, it will equal du over 2 theta. So if I plug that in for d theta and use u substitution, we'll get the integral of theta times the square root of, remember I made theta squared plus 4 the u, so I'll replace that with u, times d theta, which is obviously equal to du over 2 theta. Notice the thetas will cancel, and I get a 1/2, which I can take outside the integral since it's a constant. So we'll get 1/2 times the integral from 0 to 2 pi of, so the square root of u du, or I can rewrite it as u to the 1/2 du. Because now I can use the power rule. So we'll get 1/2 when I use the integral, or when I use the power rule on the integral of u to the 1/2, I'll get u to the 3/2 divided by 3/2, or multiplied by 2/3. So then I'll get 2 over 6, or 1 over 3 u to the 3/2. And once again, u is pi or theta squared plus 4, so I will rewrite u as 1/3 times theta squared plus 4 to the 3/2 power. And then we're going to evaluate. Our bounds are from 0 to 2 pi. So I'll write 0 to 2 pi. So then to evaluate, I'll just start by plugging in 2 pi. And so then we'll get, I'll actually leave the 1/3 outside since it's a constant, and just focus on evaluating the inside pi squared plus 4 to the 3/2. So then when I plug in 2 pi, I'll get 2 pi squared plus 4 to the 3/2 power, minus, when I plug in 0, so I'll get 0 squared, which is 0, plus 4, which is 4, to the 3/2. 2 pi squared is going to be 4 pi squared, and then plus 4, all to the 3/2 power, and minus 4 to the 3/2, and 4 to the 3/2 is equal to 8. So then what I can actually do here is factor out a 4. So then I'll get 4 times pi squared plus 1, and the entire thing is still to the 3/2 power, minus 8. But since these two are being multiplied, I can distribute the 3/2 power to both. And so then I get 4 to the 3/2 times pi squared plus 1 to the 3/2 minus 8. 4 to the 3/2 is obviously 8. So we'll get 8 times pi squared plus 1 to the 3/2 minus 8. And once again, we had the 1/3 out front, so we got to include that now. So now, finally, I'll actually, to simplify even further, factor out another 8 from here. So we'll get 1/3 times 8 times pi squared plus 1 to the 3/2 minus 1. And then I can multiply 8 and 1/3. So then the final answer for the arc length of the polar curve will be 8/3 times pi squared plus 1 to the 3/2 minus 1. So now for number 2, let's say we have the equation r equals cosine to the 4th of theta over 4, and our bounds, notice our bounds are already given to us from 0 to 2 pi. So those will be our a and b values. So go ahead, jumping into the equation here. We get the arc length is going to be equal to the integral from 0 to 2 pi, our a and b values, of the square root of r squared. So if r is cosine to the 4th, then r squared will be cosine to the 8th of theta over 4 plus r prime. So once again, if r is equal to cosine to the 4th, then r prime is going to be equal, now we have to use the chain rule here, so bring the power down, 4 times cosine of theta to the 4th, or theta over 4, and subtract the power by 1, so to the 3rd power, and then times the derivative of the inside, and the inside is cosine of theta over 4, and the derivative of that is 1/4 or negative 1/4 sine of theta over 4. So notice the 4's will cancel, the 4 and the 1/4, and so r prime is going to be equal to negative cosine of theta over 4 times sine, or cosine cubed of theta over 4 times sine of theta over 4. So if this is what r prime equals, we need to find what r prime squared is. So if we square that, we'll get a positive cosine to the 6th of theta over 4 sine squared of theta over 4 d theta. Now at first glance this might look very much impossible to solve, but this can be solved by hand. So just like this previous problem, I'm going to start out by factoring out cosine to the 6th. So let's not focus on the integral right now, let's just focus on the square root. So if I were to factor out a cosine to the 6th, so cosine to the 6th of theta over 4 times, what's left is cosine squared of theta over 4 plus sine squared of theta over 4. Now, remember that the trig identity where cosine squared x plus sine squared, or sine squared plus cosine squared, equals 1. And since we have the same thing with sine and cosine, theta over 4, cosine squared of theta over 4 plus sine squared of theta over 4 simplifies down to 1. So we're going to end up getting, and since these two are being multiplied, the square root of cosine to the 6th is obviously cosine to the 3rd. So we'll get cosine to the 3rd of theta over 4 times 1, which is obviously just still cosine cubed of theta over 4. So now that we have simplified the square root, I can now rewrite the integral. So we get the integral from 0 to 2 pi of cosine cubed of theta over 4, or cosine of theta over 4 all to the 3rd power. Now, in order to solve a cosine or sine function to the 3rd power, we can use a very simple trick here. So we can expand this. So cosine cubed we can rewrite as cosine of theta over 4 times cosine squared of theta over 4. Now, by using the trig identity, we know that sine squared of x plus cosine squared of x equals 1. So then cosine squared of x equals 1 minus sine squared of x. So I can replace cosine squared with 1 minus sine squared of theta over 4. So we can rewrite it as the integral of cosine of theta over 4 times 1 minus sine squared of theta over 4 d theta. And now what I can do is distribute cosine over to both terms. So to rewrite the integral once again, we'll get from 0 to 2 pi, which are bounds. So now cosine pi over 4, or theta over 4, times 1 is obviously still cosine of theta over 4. And then we get minus cosine of theta over 4 times sine squared of theta over 4. Since there's a minus here, we can separate these two into two different integrals. Now the integral of cosine of theta over 4 is pretty easy, so we'll just go ahead and do that one really quickly. The integral of cosine theta over 4 is just going to be 4 sine of theta over 4 minus what we have here. So in order to take the integral of this, we can use u substitution. So I'm just going to rewrite just that integral. So cosine of theta over 4 times sine squared of theta over 4. And actually I'm going to rewrite sine squared of theta over 4 as sine of theta over 4, the entire thing squared, d theta, because now what I can use is u substitution with my u being sine of theta over 4. So if u equals sine of theta over 4, then the derivative of u, or du, is going to be equal to 1/4 cosine of theta over 4 d theta. So then if I isolate d theta is going to be equal to du over 1/4 cosine of theta over 4. And since we're dividing by a fraction 1/4, we can multiply by the reciprocal. So we get times 4. So then d theta is going to be equal to 4 du over cosine of theta over 4. So if I were to use u substitution and substitute d theta back into the original integral and substitute sine of theta over 4 for u, or substitute sine of theta over 4 with u, then I'll get the integral of cosine of theta over 4 times u squared, since sine of theta over 4 is our u, times d theta, which once again is 4 du over cosine of theta over 4. Notice the cosines will cancel, and the 4 is a constant, so it can come outside the integral. So we're left with 4 times the integral of u squared du. The integral of u squared is obviously u cubed over 3. And u is sine of theta over 4. So we're going to get 4 times sine of theta over 4, the entire thing cubed, over 3, as the integral of cosine of theta over 4 times sine squared of theta over 4. So once again, the integral of cosine theta over 4 is 4 sine theta over 4, and the integral of cosine theta over 4 times sine squared theta over 4 is, now that we have evaluated it, 4 sine theta over 4 cubed over 3. So now we can further evaluate by plugging in our bounds. So we're going from 0 to 2 pi. So when I plug in 2 pi, first we'll get 4 times sine of 2 pi over 4, which is equivalent to pi over 2, minus 4 times sine of 2 pi over 4, which is pi over 2, the entire thing cubed over 3, and then minus when I plug in 0. And the good thing is when I plug in 0, everything will equal 0. So we'll just get 0 minus 0, which just cancels. And so sine of pi over 2 is 1, so 4 times 1 is 4. And then we have minus sine of pi over 2, which is 1, cubed, which is 1, times 4, which is 4 over 3. So then we'll get 4 times 1, which is 4 minus 4 over 3. 4 can be rewritten as 12 over 3. And 12 over 3 minus 4 over 3 gives us the final answer of 8 over 3.